Hello, welcome to subscribe this channel for R programming and using R for statistics. In this video, we will introduce bivariate correlations in statistics and show how to implement it in R programming. So we know correlation coefficients are just used to describe the relationships among quantitative variables, and the most commonly used correlation, called Pearson projector moment correlation, assesses the degree of linear relationship between two quantitative variables. And the formulas for correlations comes from how to calculate the covariance first. So if x and y are two random variables with joint probability distributions fxy, so the covariance of x and y can be calculated as sigma xy equals E means the expectation or mean value of the expression, which is the projection of x minus mu x is the mean x times y minus mean y. So for the discrete random variable x and y, this expression can be calculated as x minus mu x, y minus mu y times the probability distribution for each combinations of x and y value, then summation together. And for the continuous variables x and y, the covariance sigma xy can be calculated as expression of x minus mu x times y minus mu y, then times the probability joint probability distribution fxy, then take integral over dx and dy for all the available value x and y. So when we have calculated the covariance, then the correlation coefficient of x and y is just the covariance divided by the standard deviation of x and standard deviation of y. So correlation coefficient called rho xy. So if the correlation coefficient is positive, which means that one variable deviates from the mean, the other variable also deviates in the same direction. And on the other hand, a negative covariance or correlation coefficient means that one variable deviates from the mean, the other deviates from the mean in the opposite direction. So in the sampling case, usually we calculate the correlation coefficient, or for example using R to represent the correlation coefficient, equals covariance of xy divided by standard deviation of x times standard deviation of y. So we use S here. And the expression is sigma x minus x bar, which is the sample mean, and yi minus y bar, which is the sample mean of y, and take sigma for the summation of this expression, then divided by n minus 1 times sxsy. So sxsy are standard deviation of x and y respectively. So we use n minus 1 here because this is an unbiased estimate of the population variance. So this is the sampling from the sampling data. So next we will show how to calculate correlation coefficient in RStudio. So first, we create a data frame called states, which comes from the R's dataset called state.x77. So we take the first 6 columns of this data frame, then create a new data frame called states. So if we show the structure of states, it is 1 to 50 observations and 6 variables. And these are observations. Alabama, Alaska, the index for observations, and 6 columns variables. I will show the first 6 observations. For example, can see there are different states in America, and the variables are population, income, and illiteracy, life expectancy, murder rate, and so on. So if we want to calculate the covariance, you can use function COV in R. So COV states will calculate the odd bivariate covariance between variable pairs. For example, the result shows actually the 6 by 6 matrix, or so because it can be only show 5 columns, so the last column showed in the second part. So for example, population and the population to self is very high covariance, and the population to the income, this is the covariance value. And the sum, for example, illiteracy to the life expectancy is a negative, right? And you can also calculate the correlation coefficient. This is the Pearson's correlation coefficient using COR states. So now the value shows the correlation coefficient, and the maximum value, absolute value is 1 from population to itself, right? And income to itself. So if the diagonal, all the diagonal values are 1. And you can say life expectancy to the population is minus 0.068, also negative, and the absolute value is very low. And we know Pearson's correlation coefficient, it should be applied when the data should be symmetric or very close to normally distributed distribution. So if in some time when the data or the sample data is not like normal distribution and not symmetric, so in this case you can use another type of the correlation coefficient. They are Spearman's correlation coefficient, which use rank order correlation, is a non-parametric statistic, and so can be used when the data have violated parametric assumptions such as non-normally distributed. And another alternative is Candace tau, is another non-parametric correlation. And it should be used rather than Spearman's coefficient when you have a small data set with a large number of tied ranks. So both non-parametric methods use the rank order. They do not use the real value like in Pearson's correlation coefficient. They use the rank order for each observations. So in our programming, if you want to use Spearman's method, you can just use, for example, correlation coefficient, COR states, set the method as Spearman. So it will also show a 6 by 6 matrix of the correlation coefficient between variable pairs. You can also set method as a candle here. So they both will use the rank order as the input to the correlation coefficient. But we can also select, for example, if we want to select some parts of the data frame. So X, we select the 4 columns of this data frame. So X, this is X. And Y, we select another 2 columns of this data frame. So X is a data frame with 4 columns, and Y is another data frame with 2 columns. This is Y. So you can use COR correlation between X and Y. So the result is 4 rows, 2 columns. Now this comes from X variable, and these columns come from Y's variable. So these values are correlation coefficient between the value pairs. Sometimes, in addition to get the correlation coefficient value, you want to test if the correlation is significant. For example, we want to test the third column variable and with the fifth column variable of this data frame states, and to show if it is significant in the statistical testing. Then we can use cor.test function of these two variables. So the result show correlation coefficient is about 0.70. And in the first part, also show the t-statistics, because the significant test is based on a statistic called t-test. So in the t-test, the value is 6.84, and with a degree 48, degrees of freedom 48, and the important value is called p-value. So it is a very low value, minus 0.8, very close to 0. So it is much less than 0.05. So we can say the correlation coefficient between these two variables is significant at 0.05 value, significant level. Also show the correlation coefficient is 95% confidence interval. So because if we test again with another data of these two variables, it may come with different correlation coefficients, not necessarily equal to this value, 0.70, right? So there is a confidence interval. If you test 100 times, about 95% of the time will cover the real correlation coefficient. So this is the confidence interval between 0.52 and 0.82. Although for the individual test, individual result, individual range, we cannot say there is 0.95% can include or not include. For the individual range, we can only say this include the real value of correlation coefficient or not. But if we test 100 times, we can say 95% of the confidence that such kind of range will cover the real value of correlation coefficient. So in this case, in this test, the range is positive, all positive, so we can confidently in 95% confidence intervals that this range will cover the real value. So another alternative is you can use live called psych library. So just load this library, then use the cor.test function, and you can use a case called complete. So this test result will show two parts. The first part is the correlation matrix between variable pairs, 6 by 6, 6 rows by 6 columns for all correlation coefficients between variable pair. And next part is another matrix called 6 by 6. So you can see the value represents the p-value, probability value. If the value lower than 0.05, for example this one, life expectancy to the income, though this correlation coefficient will be significant. If it is much larger than 0.05, for example life expectancy with the population, so this correlation coefficient between these two variables are not significant. And if you want to download the source files to practice the code in RStudio, you can go to this link. Go to this link on GitHub. And all the videos in this playlist for R statistics will be uploaded later. you can find the source file called rstatistics.r. Thanks for watching.